We were talking about Bose-Einstein condensation the other day. What I'd like to do is to bring back something we talked about when we talked about phase equilibria. That is liquid helium. And the question today is liquid helium, or is it not, an example of Bose-Einstein condensation? There's a long history of liquid helium. It was liquefied in 1908 by Camerling Onus, but it took 25 years from then before people observed the superfluid characteristics in helium-4, liquid helium-4. Remember, liquid helium-4 is the isotope of helium that has 2 protons and 2 neutrons. Well, something in the superfluid phase has 2 characteristics. One, heat's transferred in the absence of any thermal gradient, and 2, mass flows without any driving pressure. So because of those characteristics of liquid helium, London proposed that this might be an example of Bose-Einstein condensation. So the difference between atoms in liquid helium-4 and ideal gas atoms, though, is that those in liquid helium-4 interact with each other strongly, as opposed to ideal gas atoms, which are expected to interact not at all or very little. And we would expect that the interactions in liquid helium would significantly reduce the occupation of the ground state below that of an ideal gas. But the liquid phase in helium is not stable until the temperature is very, very low. And forget about the solid phase. Remember when we talked about this in phase equilibria, you're not going to reach a solid phase in liquid helium unless you have an atmosphere of about 25 atmospheres, pressure of 25 atmospheres. Well, let's talk about Bose-Einstein condensation with regard to liquid helium. Under its own vapor pressure, helium-4 remains a liquid, essentially down to absolute zero. By the uncertainty principle, we would expect that particle would have a momentum of approximately h bar over a if, let's say, a is a linear dimension, maybe a nearest neighbor separation for liquid helium. So the kinetic energy in that case would be on the order of h bar squared over 2m a squared. As a increases, as we separate the molecules, the 0-point energy should decrease. But you might want to think of a 0-point energy as something that would produce a pressure. And that pressure tends to increase molar volume. The only compensating force then between helium atoms would be the van der Waals force, which is quite weak. And it can't compete with the 0-point energy for helium atoms. So it's very difficult to solidify helium unless you apply enormous pressure. Well, the normal boiling point of liquid helium is 4.2 kelvins. But as liquid helium is put into contact with its own vapor and cooled, the properties change dramatically when I get down to 2.17 kelvins. At 2.17 kelvins, above it, we say that this is helium-4, 1. Below 2.7, we have something called helium-2, helium-4, 2, which is a superfluid. And of course, we have sort of an equilibrium condition between those two. We have the superfluid and the normal fluid existing together. But there's no viscous interaction between them whatsoever. The superfluid, the helium-2, has 0 viscosity and has 0 entropy. So it's a lot like a degenerate Bose gas. What else? There are more similarities. Suppose I were to look at a plot of the heat capacity versus temperature for liquid helium. It would look something like this. And we have this so-called lambda transition at 2.17 kelvins. Remember we had that when we drew up the Bose-Einstein graph in the last lecture, we had a similar lambda transition happening. So this is very familiar to us. It does look increasingly like helium could be a Bose-Einstein condensate. There are some problems with this idea. First of all, the actual predicted transition temperature by London was, the critical temperature should be not 2.17, but 3.13 kelvin. So it's off by some amount. It's close to 2.17, but it's off by essentially a Kelvin. But also the details differ between Bose-Einstein condensates and helium. First of all, the Bose-Einstein calculation predicts the wrong critical temperature. Also, better calculations seem to indicate that liquid helium-4 has a logarithmic infinity at the lambda point, unlike Bose-Einstein condensates. Okay, but this isn't really surprising. Why? First of all, liquid helium is not a gas. Bose-Einstein condensates consider ideal gases that don't interact, and we know that there are lots of interactions between liquid helium-4 atoms. They're not negligible. So it's probably fair to say, maybe the most fair thing to say about liquid helium-4 is that lambda transition is kind of like a liquid equivalent of a Bose-Einstein condensation for perfect gases or for ideal gases. We mentioned also when we talked about phase equilibria that not only does helium-4 exhibit superfluid characteristics, but helium-3, which is not a boson, does so as well at much lower temperatures, at the temperatures in the order of millikelvins. Now, the explanation for how that works and why it seems boson-like is that, like the phenomenon of superconductivity, where you have Cooper pairs, the liquid helium-3 also has pairs, comes in pairs as well. So you have two liquid helium-3 atoms together forming a similar type of, well, displaying this kind of superfluid characteristic, but again, at considerably lower temperatures than does helium-4. So it takes pairs of helium-3 atoms to do this. That way, this pair is considered a boson. But in any case, whether it's liquid helium-3 or liquid helium-4, yes, the behavior does remind one of Bose-Einstein condensation, but as you can see, there are sort of limits to equating the two. Well, having said that, we can look at a couple of examples of calculations one might do. So let's tell the good news first. The good news is Bose-Einstein condensation was produced in the lab, and it happened in 1995, and it was using rubidium-87. That was the first example of a Bose-Einstein condensate, and the way they did this was they had about 10 to the 4th atoms that were confined, and they used laser cooling and trapping to where they could get the critical temperature at 10 to the -7 Kelvin. So we're talking about very, very, very low temperatures. And by doing that, they were able to achieve Bose-Einstein condensation for rubidium. By 1999, they were able to achieve it with sodium, lithium, and hydrogen gases as well. So this is not unheard of now. It is actually a thing, and people have been able to produce this in the labs. And of course, since then, there have been a lot of experiments with cold atoms and all kinds of other phenomena related to Bose-Einstein condensation. Well, that being said, let's do a couple of calculations, for example. Suppose I have a collection of 10 to the 4 rubidium atoms, and I put them in a box of a volume that's about 10 to the minus 5 meters on a side. So the volume would be 10 to the minus 5 cubed from the volume. First thing, let's calculate what the ground state energy should be. The ground state energy, of course, would be h bar squared over 2m times the length squared times nx squared plus ny squared plus nz. Well, that's just going to be 1 squared plus 1 squared plus 1 squared. And so that's going to be equal to 1.14 times 10 to the minus 37 joules, which is teeny tiny, or if you like, 7.1 times 10 to the minus 14 electron volts, if you like those units better. It's still teeny tiny. Let's find the critical temperature and compare the product of kT critical to the ground state energy. So the critical temperature I can get by this equation, 0.527 h squared over 2 pi m L squared n to the 2/3, and that will give me 0.224 n to the 2/3. So that will be 0.224 n to the 2/3 times E naught. That means my critical temperature, so my critical temperature is going to be that divided by K. And that's going to give me a value of 7.1 times 10 to the minus 14 eV here. That's going to give me a value of 8.6 times 10 to the minus 8 kelvins. So it's very, very, very small. You might ask, how many atoms? Suppose I have a temperature that's 9/10 the critical temperature. So suppose T is equal to 0.9 times the critical temperature. How many atoms would be in the ground state? Well, N 1 minus T over T critical to the 3/2 times N, which is 0.146 N, or 14 times 60 atoms in the ground state. So you would get that many atoms to participate in Bose-Einstein condensation for rubidium under those conditions. Let's look at a helium-4 example. Let's calculate the condensation temperature for liquid helium-4. And let's assume it's a gas of non-interacting atoms. It's not a gas, but let's do it anyway. So the density of liquid helium is 0.145 grams per cubic centimeter. I have 4 grams per mole is my atomic mass. And so N over V would be 0.145 grams per cubic centimeter divided by 4 grams per mole. That will give me 0.036 moles per molecules, per cubic centimeter. Moles per cubic centimeter, 2.18 times 10 to the 28th atoms. per cubic meter. My critical temperature then would be 0.527 h squared divided by 2 pi mk n over v to the 2/3. If I put my numbers in, I get what London calculated as well, 3.13 kelvins as my critical temperature for liquid helium. And of course, experimentally, it's a degree less than that. So it's probably fair to say that liquid helium is a liquid version of Bose-Einstein condensation, but is not an example of Bose-Einstein condensation. That concludes our long foray into quantum statistics. Next time we will begin with the Debye theory of solids, actually Einstein theory and Debye theory of solids, which still uses quantum statistics.